Hi everyone, so in this example we're actually looking at the centripetal force but for vertical configuration. What we have here is a remote control car that's actually going round a circular loop, okay, in a vertical kind of setting. This differs from the horizontal situation, for example a car that's rounding a bend. Okay, similar for this type of questions, you need your concept of force equations and the free body diagram. Okay, so let's look at the situation at A and B. Okay, notice that the velocity, the tangential velocity is 12 meters per second, and also the top part is 12 meters per second. So I will assume that throughout the journey of this loop, the car maintains its constant tangential velocity. This type of motion or circular motion you would say as uniform circular motion. So the other one where you actually call it non-uniform is because the tangential velocity may change in magnitude as it goes around the loop, for example. Okay, so as mentioned, free body diagram and forces. So let's look at the car's position at A. So we actually have the car having its weight mg, and it actually applies a normal force on the track. Okay, while at B, okay, so we actually have the weight again of the car, and we have the normal force that's applied by the car onto the track. Okay, so let me then now write down the centripetal equations in relation to these forces. So at A, okay, I would have NA, the normal force, plus negative mg, okay, and that would be equals to the centripetal acceleration times the mass of the car. Okay, so what happens is NA would then be equals to mv squared over r plus mg. Okay, while at B, what we have is NB plus mg equals to, again, the mass times the centripetal acceleration. So we actually get NB equals to mv squared over r minus mg. Okay, one of the first things to observe, right, is that you notice that the normal force at A, because there's a plus mg, right, its value is going to be greater as compared to the normal force of the car at B, which you can see here there's a minus mg. So if you think about it, I don't know whether you've traveled down a curve in a car. What happens is you feel like you're pushing onto the seat, or in a way the car is actually pushing down to the ground. So the normal force of the car, right, as you're going down a kind of like a slope downwards bend, it actually is putting in more pressure onto the road, which is in relation to the normal force. Okay, as calculated, NA is 30.88 newtons, while this one where you have minus mg, this actually gives us 15.19 newtons. Okay, yeah. So again, at the other part where the car is on top, if it still keeps that same tangential speed of 12, what happens when you go around the top, right? It feels like the car almost wants to leave the track. So basically the normal force actually is kind of like reducing or reduced at the top, at the higher point. Okay, I also want you guys to be aware, the same concept would go where you have the water in the bucket. Okay, so what happens is if you just imagine yourself as the water that's inside the bucket, and basically you have this normal force that is acting to hold the water in. Okay, you also have the weight of the water. Okay, so what happens is if the normal force is greater than 0, then the water still maintains in the bucket. Okay, so you can have the normal force greater than 0. So let's look at B, right? If your V tangential is greater than or your mass times V squared over R is greater than mg, then you will still have a normal force that's greater than 0. if your velocity, basically, so if your tangential speed is too slow, then what happens is the normal force will then start to become close to zero, and if it's actually zero, what happens is the water just spills out. Okay, the other one I want to show you guys is for the vertical configuration is this one here. Okay, so as you can see, right, so you can take this round circular band, right, it's somewhat like the situation at B, but there's a difference. The car is going to be above that circular portion. So again, don't worry, just look at your free body diagram and imagine what are the forces acting at that point. So what happens is you actually have your weight, and then you actually have the normal force acting perpendicular to the surface that the object is resting on. So in this situation, we actually have mg minus the normal force that will be equals to the centripetal acceleration. Mass times the centripetal acceleration. Always note that the centripetal acceleration would act towards the center of the rotation. Okay, so based on this, right, my normal force would then be equals to mg minus mv squared over r. So in this, the difference in this, right, so if you think about it, if the car is going very fast off the band, right, so what happens is you have mg minus mv. So as I mentioned, if it's very fast, right, mg minus this value, right, will reduce the value. So what happens is if the car goes round the top part of the band, right, the passenger or even the car itself would feel lighter on the road. Okay, it will be like less touching the road. Okay, for this question, we have the speed of 12 meters per second. So what happens is if we were to calculate the normal force mg, which is going to be, so imagine yourself as the person in the car, and then the normal force, this is you sitting on the car's seat. Okay, so mg in this case is 67 times g minus 67, so v squared is 12 squared, and the radius of rotation as shown in this circular circle here is 35 meters. So this gives you a value of 380 newtons. Okay, in question 63, right, so this is 62. So in question 63, okay, what happens is, so in order to feel weightless, right, what happens, it means that you are not touching the seat of your car. So n equals to 0. When that occurs, as you can see with the equation here on the left, then becomes mg equals to mv squared over r. Okay, so for the condition for this to happen, right, is when you have the car speed v equals to square root of rg, and the speed here is 19 meters per second, r being again 35, and g is the gravitational constant. So as you can see here, right, when the car moves at a greater speed, only then you can actually feel like you're going to be less or you're going to be kind of like pushed upwards in some ways. Your normal force is of you to the seat of the car reduces. Okay, just to mention, I took this question from Walker's textbook, the 162-63, and where else this 5.120, this is from Friedman's book.